Last lesson focused on lines and line segments called tangents to a circle. This lesson focuses on a line segment called a chord in a circle. A chord is defined as a segment with endpoints on a circle. So this is an example of a chord. It connects two endpoints on the circle. Quick example, a diameter would also be a type of chord because it connects two endpoints on the edges of the circle. And then, as you know, an arc is a portion of the circumference, and that'll be a term to remember for today. So this section here would be one possible arc on the circle. Now go to your postulate paper. Find the summary of congruent chord theorems. So there's several theorems that, when you put them all together, can be summed up as this. If you have congruent central angles, like these two congruent central angles that begin at the center of the circle, that tells you that the arcs above those central angles are also congruent to each other. And it also tells you that the chords that connect the endpoints of those arcs are congruent to each other. Now notice these double arrows, so that means this is biconditional. So you could start with any one of these three pairs of congruent things and assume that the other two are true. So you could start off knowing that you've got two congruent arcs out here, and from that, work backwards to figure out the central angles match and the chords match. Or you could start by knowing the chords match and use that to figure out the arcs above them match and the central angles below them match. You could use that to figure out problems like number 1. What can you conclude about each diagram? So if they tell you that the length of VT is equal to the length of RP, that's a pair of matching chords. If you have a pair of matching chords, you could assume that the central angles below them match. Angle VDT would be congruent to angle RDP. And you could also assume that the arcs above the matching chords are congruent to each other. Arc VT would have to match arc RP. Pause here and try part B and C on your own. Check your answer for part B. To begin with, they're telling you these two central angles match, so therefore both the chords GF and GK are congruent to each other, and the arcs GF and JK are congruent to each other. Here's part C. They're telling you the central angles match. From that, you can work to the chords above the central angles being congruent to each other, and the same with the arcs above those central angles. Now go back to your postulate paper. Find theorem 12.7. Try to draw two chords that are about the same length. So this is a biconditional, an if and only if. So if you happen to notice you have two chords that are the same length, they're congruent to each other, you could assume those chords are equally distant to the center of the circle. A quick reminder, you'll often see any segment that's measuring distance connected to a right angle because the shortest distance between a line and a point is always perpendicular to the line. So this is showing that the segments are equidistant to the center of the circle. And it's biconditional, it works backwards. If you notice you have two chords that are equally distant to the center of the circle, then you could assume the two chords are equal to each other in length. Pause here and see if you could figure out all of question 2 on your own using this rule. Go ahead and check your answer in question 2. Because these two chords are equidistant, 9 units away from the center, then they're equal. So if this section is 12, the whole thing's 24, and the opposite chord would match it. X equals 24. Here you have congruency marks on the pieces of the chords. So you know the chords are equal lengths. You could use that to figure out, working backwards, that they're equidistant to the center of the circle, x equals 3.2. And here, because these chords are equidistant to the center of the circle, they're equal. So this whole chord is 10, so is this whole chord. But see how the x is off center? That means you just want half the chord, x equals 5. Now go back to your postulate paper. Last theorem. A summary of the perpendicular bisectors and circles theorems. A diameter, this blue line, try to draw it so it's going through the exact center of the circle. A diameter. A diameter is perpendicular to a chord if and only if it bisects the chord and the arc above it. So this diameter is going to make a perfect right angle, be perpendicular with this chord, as long as it's bisecting the chord, cutting it into equal halves, or bisecting the arc above it, though more often you'll see it with the chords. And it works backwards, it's biconditional. If you see that a chord is bisected, you could assume there's a right angle here where the diameter cuts into it. And also just add marks to show it also works if if you're bisecting the two arcs. If you're bisecting the arc into two equal arcs, that's another way to figure out that the chord is making a right angle. Pause here and use this rule to figure out question number 3. So for question number 3, if you got a equals 6, great job. Because of the right angles where these radius, which are part of diameters, hit the chords, because they're perpendicular to the chords, we know they're bisecting the chords. And we also know that they're equidistant to the center of the circle, so we know the total of both chords has to match. So if this is 12, the missing piece is 6. This one takes a little bit more work. You could use the fact that this radius is making a right angle to this chord to figure out first that it's bisecting the chord. So if this section is x, the other half has to match it. There's an x here. And that right angle also helps you know how to solve, because you could use Pythagorean theorem. X squared plus 8 squared equals 17 squared, and solve from there. And that's going to be one of your go-to techniques for the rest of the page. There's going to be a lot of Pythagorean theorem going on. I want you to pause here and see if you could figure out the whole rest of the page. Check your answer for number 4. You should get square root of 61, or you could just round that to about 7.8. Here's the idea. If the whole chord is 12 and it's being bisected by this perpendicular radius, then the side of the triangle here is 6. 5 squared plus 6 squared equals x squared, and you could solve from there. Now, B is interesting. The thing I want to point out about part B is that the radius length from the center of the circle has to be the same no matter what direction that radius is going in, right? So no matter where you draw the radius, they're all 9 units long. So if this radius is 9, so is this radius. That's also working as hypotenuse of your triangle. So you could say x squared plus 5 squared equals 9 squared, and solve from there. If you haven't yet finished the rest of the worksheet, pause here and complete it. Check your answers for number 5. One thing I want to point out for part A, see how the x is centered on the chord? So they want the whole chord length. So you can make up your own variable name for the part of the chord that's actually a side of the triangle. But once you get the side of the triangle, don't forget to get the whole chord, you have to double it. So depending on where you rounded, you get around 15.8 or 15.9. Part B, remember that idea about the radius being the same length in all directions? So you could draw your own radius from the center of the circle to the edge of the chord here and label that a length of x. And then if this whole chord is 9, then the side of the triangle you've drawn would be 4.5. So you could say 1.9 squared plus 4.5 squared equals x squared for the hypotenuse, and solve from there. For your last question, you should get x equals 5. Oh, that should have been an equal sign. Oh. Great job, everybody. When you're done with the notes, don't forget to turn in a picture of your notes on Schoology.